So this is like a snapshot. So step 1 again, guess UVP at all cell centers. I've already told you this. Okay, and that's really nothing but U0, V0, P0 because my K equal to 0 at that iteration. Okay, now one thing, okay, I'll get to that in a moment. So note, Navier-Stokes equations are nonlinear, therefore iteration is unavoidable. I already told you this. Any iterative solution procedure will always require an initial guess. Okay, the initial guess must not alter the final solution. Very important to understand. If you come to me and tell me I used a different initial guess and I'm getting a different answer and it shows convergence, okay, then I'll say something is wrong in your code. Okay, now careful again, we are talking about steady state solution and I'm not talking about the initial condition as in a transient problem. Okay, this is initial guess. All right, a guess precisely means what that word signifies. It's a guess. It should not affect the final answer. It has no physical significance. Okay? Now, I'm also saying the initial guess should be physically meaningful. Why? Because you're solving conservation equations of mass and momentum. If you start with a wild initial guess that violates all conservation laws, you're not helping the process. Okay, you're just trying to bully the process. So give it an initial guess that helps. Okay, the most common initial guess that I and everybody else in the world uses most of the time is zero velocity, zero pressure. Okay, now sometimes that guess may not work, you know, but for the most part it works fine because the moment one of the control volume faces sees an inlet velocity, those zeros get replaced. Okay, but if you have a problem where, you know, zero velocity keeps everything zero, nothing changes, then maybe it's difficult to jumpstart. You may have to start with some value. Okay, but for the most part, zero works fine, especially for pressure. Because when you start a problem, let's say you have a complex three-dimensional flow problem, you have no idea what the pressure field is going to look like. Okay, so no point trying to guess it. Yeah, sure, if it's a channel flow, you say, okay, my pressure is a linear profile for starters, for a guess. That's fine, but most of the time you'll have no idea what the pressure field will look like. Okay, so the safest thing to do is to start with uniform pressure. Next step is to calculate the link coefficients of your momentum equations. So you already have the equations. I'm not going to belabor the points. Now next, then after you've calculated links, you calculate pressure sources because again, you know your pressure, guessed it already. Okay. The link coefficients, once you calculate in step 2, I want to emphasize this, remain unchanged during an outer iteration. Do not change it anymore. Okay, until you get back to step 2 again. You need to save and store the link coefficients once calculated for the entire outer iteration. Why? I want to draw your attention to this. Look at these. Pressure links require momentum links. Okay? So once you calculate your link coefficients at each cell, A0, A east, A west, A0, A south, for both momentum equations, you better store it because you're going to need them to calculate your pressure links. Cannot throw them away. Okay? Everybody get that? That's why I said stored them. Now, you know, I've written them in terms of ij index. So what does this mean? This means the diagonal coefficient at the node I plus 1 comma j. This means diagonal coefficient at the node I comma j, and so on. Now, of course, the A0, A south, A east, A west, you don't need for the simple algorithm, as you can see from these formulas. You just need the diagonal of the momentum equations, okay? Later on, when we get to simple C, you will see that you will require all those coefficients. All right? For simple, you don't need that. You just need the diagonal, as you can see here. But both X and Y momentum. And they are different, by the way, you know, on a staggered mesh. Okay. So that's why we are saying here, when we get down here, that you need to store the link coefficients. Do not throw them away. Permanent memory. Okay. All right. So this is the start of the outer iteration loop right here, where I'm calculating the link coefficient. Okay. Now I solve my x momentum equation iteratively. This is inner iteration, and I'm naming another counter I as opposed to k. Okay. Now you're going to solve this in correction form with inertial damping. So what does that mean? That means I've introduced this inertial damping factor here, and this is now my new diagonal. This is the linear form of the momentum equation that I'm going to solve iteratively. And since I'm solving it in correction form, the right-hand side has the residual of the momentum equation rather than the pressure source itself. And these corrections I'm denoting by a tilde. These corrections, the u tilde is different from the u prime we talked about earlier. U prime is the correction in the outer iteration between momentum and mass conservation. U tilde is simply a correction in the inner iteration of the momentum velocity itself. Okay? This simply shows up because we are solving the equations in an iterative way rather than using Gaussian elimination. All right. So typically we will solve this equation to partial convergence. I already said that 1 or 2 orders of magnitude reduction in residual or a couple of sweeps. Okay, by couple of sweeps, I mean if you're using ADI, for example, you would use maybe 2 row sweeps and 2 column sweeps, and that's it. Okay. Link coefficients stay unchanged during the solution. I already mentioned this. I'm emphasizing this because you might think, well, I'm updating U. Why don't I go ahead and change my link coefficients? No, don't. Okay? That would make the mathematics inconsistent. All right? Update your U after you solve for your correction, and this is nothing but you're simply saying that, okay, my U hat, which is the velocity field that I get by solving the momentum equation, is whatever I had in the previous iteration plus the updated value that I get by solving the momentum equation. This is a correction, remember now. Okay? So this is the first of 2 updates to the velocity field. Okay, this first update, as I said, is intended to make the velocity field satisfy momentum conservation, at least partially. Why partially? Because here we have partial convergence, number 1. Number 2, this equation is the linearized form of the momentum equation. It's actually a nonlinear equation, but this first rho u, rho v, we are still treating it at iteration k. Okay, so it's a linearized form of the equation, and that's why this is partial satisfaction of momentum conservation. All right, everybody with me so far? All right. Next step, same thing, y momentum. So I'm not going to spend too much time on this. You now have residual of the y momentum equation. V tilde is my inner loop correction. Same thing, you correct, and this satisfies the y momentum equation partially. Okay, so now we have u hat and v hat. These are ready. This is the velocity that I've gotten by solving the momentum equations. Okay, what do I do with that? Now I'm going to calculate my link coefficients for the pressure correction equation. These require link coefficients for the momentum equations. Okay, I already showed you that the A naught P, for example, requires A naught X and A naught Y. Okay, and then with that velocity field that I just calculated in step 4, I'm going to calculate my mass imbalance. So I solve my momentum, I take the velocity field and calculate mass imbalance in each cell. That becomes basically my driver for the pressure. Okay, so step 6, you solve the pressure correction equation. Now, I have a couple of notes here. Solve this equation as is, i.e. do not convert to correction form of an equation that is already for a correction. Okay? Since this is a Poisson or diffusion-like equation and does not require inertial damping. Okay? For those of you who have taken numerical methods with me, I've already explained this, that if you have a diffusion equation, you should not use inertial damping, because the only thing that it will do is slow down convergence. It's not necessary, because in a diffusion equation, by definition, the Scarborough criterion is satisfied, okay, and the eigenvalues are always bounded. The spectral radius is pretty close to 0, or it asymptotes to 1. It never exceeds 1. Okay, so for a diffusion equation, you don't need inertial damping, and you should not be using inertial damping. If it is blowing up, then there is something else wrong in your code. Don't try to use inertial damping to fix it. All right. This is also solved to partial convergence, because as I said, once you solve x momentum, y momentum continuity, there's no point doing it to machine accuracy, because you have to go back and do it again. However, the general observation that people have over the last 50 years is that mass conservation should be much tighter than momentum conservation in the simple algorithm. Okay? So they typically would use much tighter convergence criterion for this pressure correction equation compared to the momentum equation. All right? So instead of 2 to 3 orders, they would typically use 4 orders of magnitude reduction in residual. Or instead of 2 to 4 sweeps, they would use 20 sweeps, and so on. Okay? So tighter convergence. One thing you have to realize is that mass conservation is really at the heart of everything. To give you an example, if I have, let's say, an isothermal flow, okay? Let's say temperature same everywhere. So, we were talking about this channel flow problem. Let's say I have 300 Kelvin here, 300 Kelvin at the walls. Okay. Now, obviously, if I solve the energy equation, I should get 300 everywhere. Okay. But guess what? If you don't satisfy mass conservation in other words, you've already solved the fluid flow problem and it does not satisfy mass conservation, you're going to get either hot spots or cold spots in that computational domain. For the simple reason, if I take energy balance in a control volume, there's flow coming in here at 300 Kelvin, flow coming in here at 300 Kelvin, flow going out here at 300 Kelvin, flow going out here at 300 Kelvin, but the mass itself is not conserved. So if I look at energy conservation, which is m dot times the energy it's carrying, that is also violated. So I'm going to end up getting hot spots or cold spots. Okay? So if you do not conserve mass, you have absolutely no hope with anything. Same thing for momentum. All right? It's at the heart of everything that we do for these sorts of problems. So that's why there is so much emphasis on making sure that this pressure correction equation, which is really a representation of mass conservation, is done more tightly, more accurately. Okay? And then the final step here is you update your pressure and velocity fields, and I have already talked about this. You apply inertial damping. This is the second of 2 updates of the velocity field. Okay, so the first update was when I solved the momentum equation. I updated it with the correction, and now I'm doing the second update, which is intended to make it satisfy mass conservation. Okay, and this is, of course, the only update of the pressure field. Linear relaxation or damping is used for both corrections. We talked about this. And then finally, you monitor convergence. Okay. And repeat steps 2 to 7 if necessary. Step 2 was calculation of your link coefficients. So after you've done this part, you check your convergence and then you go back all the way and recalculate now your link coefficients again. That's the only time you recalculate link coefficients. Okay. Any questions? So this is the end of your outer iteration loop. All right. Let's talk a little bit about monitoring convergence, because now obviously we have 3 things. It's not just one PDE you're solving 3 PDEs in a sense. So As before, we define our residual as the L2 norm of the discrete linear system of equations. So that doesn't change, okay? Your residual definition is still the same. All terms of the equation brought over to one side, squared and added, okay? Do not change that. However, in this case, we have three separate residuals for the three sets of equations we need to solve, okay? If you go back, steps 3, 4, and 6, we are saying, so 6 is this equation, you're solving iteratively, okay? 4 is your y momentum equation, solving iteratively, and then 3 is your x momentum equation, again solved iteratively. So we have three sets of linear algebraic equations, we're solving iteratively, okay? So the question is, how do we monitor convergence and what do we do? So, important points to note about the momentum equation, they are nonlinear. Okay, in steps 3 and 4, we are solving the linearized form of the momentum equations. Okay, and even if we take the linearized form to machine accuracy, that still does not guarantee that momentum conservation has been satisfied. All right. Every time the mass conservation equation is solved, velocity will change, and that will automatically violate momentum conservation again. All right, so you have to do all of this simultaneously, and the residuals will jump back. In fact, you will see this. Here is what you will get for your residuals, okay? If you plot, you will see this yourself. Typical residual plot will look like this. This is in log scale, okay? That's what it'll look like. And sometimes, and this is very classic, especially at high Reynolds numbers, what you will see is as follows. Your x momentum may look like that. Your y momentum may look like this, again, sort of in phase. Okay? And your continuity may look like this, out of phase. Because every time you solve continuity, you're destroying momentum conservation. Every time you solve momentum conservation, you're destroying mass conservation. Okay? But since they're working in unison, ultimately by the time you get here, and so what will happen is this will happen for some time, and then you will start getting, towards the tail end, you'll start getting these oscillations die out and linear convergence. Okay? So what is happening is that you're correcting velocity, but as you are getting closer and closer to overall convergence, yes, mass and momentum conservations are disturbing each other, but the disturbance is so small that it doesn't matter anymore. Okay? All right. So, some points to note about pressure correction. Pressure correction equation does not have a direct physical meaning. Okay? Yes, it is derived from the continuity equation, but you can't look at that equation and say, okay, this is mass conservation. No, I mean, it's derived from mass conservation. It doesn't really have a physical meaning. It is an artifact of mass conservation. Okay? So rather than use its L-squared norm directly for monitoring convergence, we use the L-squared norm of the right-hand side to monitor convergence. Why? Because the right-hand side is mass imbalance, right? So instead of using the whole pressure correction equation, if I just take the right-hand side and calculate the L-squared norm of that, that simply indicates how much mass error I have in the system, mass imbalance error. Okay? So in other words, if you go back here, okay, right there, okay? So if I take this quantity here and calculate that at every outer iteration and monitor that, once that goes to 0, then that means I've satisfied mass conservation. So I don't really need to monitor the pressure correction equations. Let me just wipe this out so you'll see for yourself what's happening. So what we're doing is Yes, sure. We can. You know, we have this is equal to negative m dot, right? So we can say, okay, my residual is a naught p naught prime plus summation of a neighbor p prime neighbor plus m dot summed over all the cells. I can say that's my residual, but instead I'm saying, okay, let's just forget about these terms because they don't have any physical meaning. I'm simply going to calculate the L2 norm of the mass imbalance. All right, because by definition, once this converges, the p primes will be 0 anyway. If the mass imbalance goes down to 0, the p prime should also go down to 0. Okay, so this is just a common practice. People use the mass imbalance L2 norm as the quantity that they monitor for you know, the continuity equation, rather than take the L2 norm of the pressure correction equation itself. Okay, but you are free to do that if you wanted to. Okay, there's nothing that prevents you from doing that. Okay, so let's see. We already covered this. Yeah. So that's what I'm saying here, that if this quantity is brought down to a small value, that would imply that mass conservation has been satisfied. So at what points in the overall algorithm should the residuals be calculated and stored and of course monitored? So X momentum, we are saying right after the first iteration in step 3. Okay. Now, let me just, instead of scrolling, let me break out of this and it's easier to do. Go back here, or maybe we'll, yeah, there is step 3. So step 3 is solving your X momentum equation. Okay, so what we're saying here is at the very first iteration, so suppose I have, I start my whole iteration process. Okay, I have a guessed velocity field. From that guessed velocity field, I'm going to calculate the residual of this equation. Sorry, I have to put this in PowerPoint mode. Yeah, I calculate the residual of this equation. Okay, that basically tells me how much momentum imbalance I have, because at this point I haven't even solved the momentum equation. You understand? So I started with U superscript K, my guess. Okay. I'm using that U superscript K and I'm calculating this residual right here. That residual uses U superscript K not only for the link coefficients, but it's also using that same U superscript K for the velocity that it's multiplying the link coefficient with. Okay, because that second velocity hasn't been changed yet. Okay, so that tells me how much momentum imbalance I have at that outer iteration. The moment I solve the linearized equation, that value changes. Maybe my momentum comes down. Okay, but I'm not going to bother about that. I'm simply monitor it at that point. Okay, next iteration, when I come back and do the same thing, I'm actually calculating the residual at UK plus 1. Okay, or iteration K plus 1 for the X momentum equation. So every time I go down one complete outer iteration and come back and calculate the residual at the beginning of the solution of the momentum equation, I have how much momentum imbalance I have. Okay, so that's basically what I was saying here. That right after first inner iteration in step 3. Okay, now remember, you're already calculating the residual to solve the momentum equation in step 3 because you're solving it in correction form. So you're not doing any extra work. You just take the residual vector square and add it up to calculate your L2 norm. That's all. It's not like you're doing any extra work. Okay. Same thing for Y momentum. You do it at the first iteration in step 4. Okay. And then for pressure correction, we already talked about it. right after step 5. So this is basically the first iteration of the, what happened here? So here is step 5. So step 5 is solving the, let's see here, there we go. So we are solving the, we are calculating the link coefficients and the mass imbalance. Right after we calculate the mass imbalance, we calculate the L2 norm of that. All right. So that's, those are the 3 steps that we are talking about here. Okay. So monitoring of the convergence, step 8 implies that all 3 residuals must go below the tolerance. So, you know, some sample coding logic that you can use. You can say, okay, if R2X is less than epsilon X and R2Y, notice the operative word here is an and. If any of those are not satisfied, then you go back and do it again. Just satisfying one of them is not enough. Alternate logic would be you use an OR logic, but in this case, you're instead of using break, you're doing continue. Okay, so if any of them are above the tolerance, you continue. All right. What values of tolerance should we use? Common question. There is no universal answer. This is very problem dependent. So, you know, if you're doing flow with hundreds of meters per second, then obviously your residuals will be very large to begin with. Okay. Whereas if you're doing creeping flow at 1 centimeter per second, then your initial residuals will be very small. So really, it depends on that. And so that's why people often use, like I told you a couple of lectures ago, a normalized value where you look at, okay, the normalized residual defined as this, where this is R2 divided by the maximum value up to that point. Okay? And you bring it down by whatever orders of magnitude you want to. Now for your homework, you know, I will ask you to use absolute tolerances because those are just some numbers I got when I solved the problem myself. So instead of having you do all these things, making it complicated, I'll just have you use an absolute tolerance. Okay, but in general, one should use a normalized tolerance. So here's the final flow chart for simple. So we start with a guess, k equal to 0, calculate link coefficients and sources. Okay, so here are your momentum links and your sources. Sources have pressure. All right, you solve your x momentum. Before you even solve it, you have to calculate the residual and you store that residual. Okay, so that's the residual you store. Now here you're doing inner iterations. Same thing with the y momentum equation. Before you do anything here, solve this equation, you store the residual. Okay. Once you've solved the momentum equations, you calculate your link coefficients for pressure correction. So that's these two guys and your source terms, mass imbalance, essentially. Okay, so you take the velocity field, plug it in, satisfy your, calculate your mass imbalance and your pressure links. Now the pressure links, of course, will require the momentum links themselves. Okay, so that's why you have to store these guys. Then you solve your pressure correction equation. Okay, and before you even solve it, right here, you're storing the L2 norm of the mass imbalance. All right, and once you've solved your pressure correction equation, you correct your velocity and pressure. So now this velocity is basically a correction to the velocity that you got after solving the momentum equation, which satisfies mass conservation as well. And then you check for convergence. If the answer is no, then you move over to the next iteration. If the answer is yes, you post-process results. Okay? So that's the overall simple algorithm. So let's talk a little bit about pressure. Okay. So a couple of important points to note. First of all, the pressure gradient or difference is what drives flow, not the pressure itself. Okay. So you have to be careful, or not careful, but you can use that to your advantage. Okay? This simply means that, for example, if I use gauge pressure versus absolute pressure, it's going to amount to the same thing, because difference in gauge pressure is the same as difference in absolute pressure. Although gauge pressure itself is not equal to absolute pressure, right? But their difference is the same. So I can get away with using gauge pressure instead of absolute pressure. Okay. Now, how does that work mathematically? Well, it's very simple. So suppose you look at the Navier-Stokes equation, X momentum equation I've written down. So this is just brought over from a previous slide. And now, of course, you know, I haven't introduced the incompressible assumption. So the full Newtonian relationship is right here. But that's not our emphasis here. What I want to show you is that, okay, suppose I write pressure as some reference value plus gauge pressure. Okay, reference value could be anything. It could be 1 atmosphere, 5 atmosphere, it's up to you, all right? If you do that, and now you look at that term, dpdx, dpdx is ddx of pref plus pg. This is a constant quantity, some reference value, okay? So therefore, its derivative is 0. So you see, I can actually take this and substitute it in here. So my entire Navier-Stokes equation now has gauge pressure. It has no pressure in it, okay? That's the same thing as saying difference in gauge pressure is the same as difference in pressure, and so we can use them interchangeably, okay? There is one place you have to be constant, you have to be careful, and that is when you compute density, okay? Remember, this guy, if you're using, for example, ideal gas law, this is P over RT, right? Now, this is absolute pressure. You can't use gauge pressure that you calculated out of your code directly in there to calculate density. That would mean reference pressure is 0, basically. Okay? So be careful with that, that you need to still be careful when you compute density. Keep in mind that what your code has calculated is the gauge pressure. Okay? So all that means is you simply add the reference pressure to that and then compute your density. All right? Now, what does that mean? What are the benefits of using this? Why do we want to do this? Okay, you know, obviously we don't want to introduce a new complexity unless there's a good reason to do that. So here's the reason why we want to do this. So the vast majority of CFD computations are performed at pressures close to 1 atmosphere. Okay, because we are looking at terrestrial applications, right? Sometimes you can have higher pressure, but let's say 1 atmosphere or something close. Okay. We rarely compute close to vacuum, okay? I mean, if you've gone down close to vacuum, that would be a very, very special scenario that you're looking at, because getting close to vacuum itself is very tough in practice, all right? So vacuum is never our reference pressure. Most of the time, it's close to 1 atmosphere. Now, if you think about 1 atmosphere pressure, that's almost 10 to the power 5 Pascal, okay? So it's 101,325 Pascal, large number, okay? In contrast, if I now look at pressure drop in most engineering applications, it is at most a few tens of pascals. So if I take a long pipe and look at water flow, you will probably find that the pressure drop is few tens or few hundreds of Pascal at most, okay? If you're looking at gas flow through the same pipe, it's going to be in the order of 1 Pascal or less. Okay, so what we're saying is that if I have a pipe, long pipe, let's say, okay, the delta P here is close to 1 Pascal, whereas the absolute pressure is close to 10 to the power 5 Pascal. In other words, here it will be 10 to the power 5 plus 1 or plus 0. Here it will be 10 to the power 5 plus 1. Okay? Very minuscule change. These small changes tend to get lost in numerical precision when we deal with numbers as large as 10 to the power 5. Okay? Especially if you're looking at pressure drop over a tiny cell. That's going to be in millipascal. You know, if I have 1,000 grid points along the channel and the net change is 1 Pascal, then within each cell I'm going to get a millipascal. And if you try to capture a millipascal in the context of almost a megapascal, then that's a problem, okay? So that is why, so what I'm saying here is that if we, let's say, set an outlet boundary condition of 1 atmosphere, okay, and the pressure drop is less than 1 Pascal, then the inlet pressure will be registered in the 6th decimal place, which is what I'm talking about here, okay? And that's dangerous numerically, because very often you might have a tiny little cell where the pressure drop is really small and it just gets lost in precision. So then you get very weird results, because, you know, you're trying to correct for pressure, but it's lost in numerical precision. All right? So this is why we use gauge pressure, because if we use gauge pressure, this number is gone here. I'm doing all my calculations with reference to 0. Okay, I set my outlet pressure to 0, which means it's at 1 atmosphere. Okay, and then whatever the code calculates, it calculates. That's simply your gauge pressure. Okay. So this is the idea behind using gauge pressure for pressure when you set boundary conditions. All right. There is nothing which prevents you from using actual pressure. It's just that it's numerically not favorable. All right. So here are two cases. So suppose you're thinking about setting up a CFD problem, and these are two cases. Gas flow in a channel with outlet pressure of 1 atmosphere versus 2 atmosphere. What's the difference in the setup? Here's the difference. So case 1 setup, you would set gauge pressure to 0. Okay. And then the inlet pressure obviously will be calculated by the code, whatever it is, depending on the frictional forces. But when you calculate your density, you're going to use this formula where your reference pressure is that much. Okay. Same problem, case 2, if I set it up, my outlet pressure hasn't changed. It's the same, 0 back pressure, 0 gauge pressure, okay? But again, your density you will calculate using that, where my Pref is that. What does that mean? That means even though the setup of the boundary conditions for pressure are identical in the two flow problems, here I have a much larger, much smaller mass flow rate than here, because as you can see, the density here will be twice as much, almost. Okay? In other words, I'm pushing more mass at the same flow rate if I have 2 atmospheres versus 1 atmosphere. So let's say my inlet velocity is 1 meter per second. That means I'm going to be pushing twice the amount of mass because my density is 2 times larger in the second case, almost. Okay? So that will also result in a bigger pressure drop because, you know, I'm trying to push more fluid through the system. But that's the setup in terms of, you know, how you set it up when you finally want to solve it. So in terms of solution of the equations don't even realize that these are two separate problems as far as the boundary conditions are concerned, except in the step where you calculate your density. Okay. Now, if this is a liquid and you're not using an equation of state, density is constant, then this problem and that problem, they're identical. Okay. There's no difference. If you look at water flow in a pipe where it's dumping out at 1 atmosphere versus 2 atmospheres, it's going to be an identical solution. The solution, the inlet pressure may be 1 atmosphere plus 0.002 atmospheres at the inlet. The same thing will happen for the other problem. You'll get 2 atmospheres plus 0.002 at the inlet. Identical solution. There's no difference. Because you've kept your density constant also. Okay? So if somebody tells you, okay, I want to solve this problem in a pipe with water flow, 2 different cases, 1 atmosphere versus 2 atmospheres, okay, everything else same, you should immediately tell him, well, your answer is going to be the same. You'll get the same pressure drop in both cases. Okay, because your density, viscosity, everything is the same, your dimensions are the same. The fact that one is at 1 atmosphere versus the other is at 2 atmospheres doesn't make any difference. Okay, if it's a gas, of course, it would make a difference because then your density would, in one case would be almost twice as much. All right.